Hi, we are about to start 8.3, which is the last section in Chapter 8, and this is going to be on binomial settings. Now, before we get started, remember that we did already study combinations and permutations. Permutations are when order matters, and we have the formula for that, so you want to make sure that you have that written down in your notes. And combinations are when order does not matter. So once again, permutation, order matters. That's if I were to pull, out of a class of 18, I wanted to select 4 of you to get different prizes, whether it's a $100 gift card or a $50 gift card or $25 or something like that. Since all of our prizes are different, order matters when you're drawn. So of course you want to get the highest prize. So that would be an example of a permutation. And a combination is an example, is one where order does not matter. So once again, if I have 18 students in my class and I decide to pull 5 of them to get a no homework pass, well then it doesn't really matter if I pick you first or second or third or fifth, you're still going to get that no homework pass. So that's when order does not matter. So permutations and combinations are formulas that give us the probability that something is going to happen. Okay, and now we're going to do one more, and this is called binomial. All right, so binomial settings occur when we have independent trials, which means the probability does not change each time I go, which is very, very important for you to check, and we record the number of times that a particular outcome occurs. So here are some examples of binomial settings. First one, toss a coin 5 times and count the number of heads. Well, we know it's independent when you flip a coin because the coin doesn't remember if it was heads or tails last time. And we have a set number. We have 5 times we're going to toss. And we're trying to count how many number of heads we get. So that's recording the number of times a particular outcome occurs. All right, another one is paper, rock, scissors. Or rock, paper, scissors. I always say it wrong. So if you're going to play a game 20 times with your friend and you're counting the number of times you win, we're assuming you're not cheating or your friend's not cheating, so that it is an independent trial. And we have set 20 numbers, 20 times you're going to play. And then the number of times you win is the number of times of the particular outcome that you want. And then the last one, the number of female babies born out of 100. Once again, we're going to assume that gender birth is independent. So it's not like you have one girl baby and you can't have any more. That's not how that works. And we have a set number, 100. And we're trying to count how many females are born. So that is a particular outcome. So it's very important that we check to see if something is binomial before we even proceed, because sometimes you read it and it sounds like it may be binomial, but maybe it fails a condition. So there's an easy way to remember what the conditions are. So I want you to think the word bins. So we've used a lot of words in stats to help us remember things. So we're going to use bins to help us know if something could be binomial or not. So first of all, in bins, the first B stands for binary, meaning it can only have 2 options. It can either be a success or it can be a fail. So in our babies born, if you were a girl, that was a success, and if you were a boy, that's a fail. Not a slam against guys, that's just how we set up our trial. I is independent, and we've already talked about that. What we're saying is basically each trial does not change the next trial. So when you have a girl baby, it doesn't use up the number of girls that could possibly be born in the world. Or if you flip a coin, it doesn't use up the number of heads you could use. So you always want to check that something is independent. In, there should be a set number of trials. So they should tell you somewhere how many times they're going to do it. So if they say, oh, we're going to flip a coin 10 times, that's a set number of trials. But, and this is important, listen, if they say we're going to keep flipping until we get ahead, that fails this condition, because keep flipping until I get ahead, well, that could be the first try, that could be the 5th try, that could be the 100th try if we had a very unlucky streak. So since there is not a set number of trials from the get-go, it would fail. So it can't just be go until you get something. it's got to be a predetermined number, like I'm going to shoot it 10 times, or I'm going to roll the dice 4 times, or something like that. And then success, the probability of success must be the same. So if the success is the same each time, then it's going to meet that criteria. And what I mean by probability of success is, like when we flip a coin, the chance of you getting ahead is 1/2. Or if I have a dice and the probability of me getting a 6, that would be a 1 in 6 chance. So basically the success probability can't change, which has a lot to do with independence, but it also helps us write down a number for our success. So let's check and see if this is actually a binomial. So we're going to shuffle a deck of cards, and we're going to turn over the top card, and we're going to put it back in the deck and reshuffle. And we're going to do this 10 times, and we're going to count the number of aces that I see when I flip this flip these cards up 10 times. So let's check. Is it binary? Yes. But there's lots of cards. True, but we break it down into an ace and a not ace. So if it's an ace, we put a number in this category, and if I get any other card, I put it in the not ace category. Is it independent? Yes. Now, normally it's not. If you would just take a card out and leave it out, you've changed the probability, because now we're drawing out of 51 cards instead of 52. It changed the denominator. But because we put cards back, it is actually independent. Is there a set number of trials? Well, yeah, it said do this 10 times. So that's set. And is the probability of success the same? Well, if you remember, there are 4 aces out of 52 cards. And since I put the card back after I draw it and I reshuffle it, I still have a 4 out of 52 chance that I'm going to get an ace. So yes, my probability of success does stay constant. However, if I did not put the cards back, that would make the I and the S fail, and so it would not be binary. So example 1 is a binomial setting. So right now we're not even doing any math, are we? We're just figuring out what are the conditions before we can actually do some math. Let's look at another example. Shuffle a deck of cards, turn over the first 10 cards one at a time, and count the number of aces you observe. Okay, so let's take a look at what we have here. So we're going to keep our bins up here because we always want to check bins. And so first of all, do you think it's binary? Do we have 2 outcomes? Well, sure, we still have aces and not aces. So we can still count that as binary. Is it independent? No. How is this different than the last one? Well, this time we don't replace the cards. And since I don't replace the cards, that means my denominator changes, and that means the probability changes. So it's not independent. It now depends on what you drew. So if your first 3 cards are aces, obviously if you didn't put them back, there's only 1 ace left in that deck. And after you get the 4th ace, there's no more chances of you getting aces. So the most you could get is 4 aces. So your probability definitely changes. Is there a set number of trials? Yeah, it's 10. And is probability of success the same? No. Once again, the denominator will change each time. So is this binomial? No, it is not binomial, and the reason why is it fails. Now, usually you don't need to check all of these. You only need to check until you get 1 no. So I could have really stopped here at I. I could have said it's not independent and been done with it and just said, okay, it can't be binomial. But I went ahead and showed all 4 so you could see that 2 of them actually were yeses and 2 of them were actually nos. But really, if only 1 is a no, then the whole thing won't work. All right, let's look at another binomial experiment. There's a special promotion going on with a soda company, and under the lid of bottles is printed either please try again or you are a winner. The company says there is a 1 in 6 chance of winning, and you and 5 of your friends buy a bottle to try to win. So a total of 6 of you are buying a Coke or a soda or whatever it is. What is the probability that none of you will win? So first of all, we have to check, is it binomial? Is it, first of all, binary? Do you have two options? Yes, because you could either win or you lose. Those are the two options. Is it independent? We're going to say yes. Now, this one's a tricky one because, yes, when you buy a bottle of Coke, there's now less soda out there in the world. But because they make millions and millions of these things, really, if you use one, you haven't really changed probability. And plus, they're probably going to make more to replace the one that you used up. So that's why we say yes. You can say yes to independence when the population is so humongous. If you take, a couple out, it's not really going to change the probability. Our card example, it did matter because we only had 52 cards. And so when you start taking away from 52, it does bring that denominator down pretty quick. Do we have a set number of trials? Well, this one is weird because I'm not buying several bottles. I'm just buying one, and each of my friends are buying one. And so actually that comes right there. Since 5 of my friends and I are buying one, that is 6 trials because we each are buying one. And the probability of success, well, they told us that the probability of success is 1 out of 6. And once again, given that they're not lying to us and they've told us the truth and they haven't used up all the winning pieces, it should be okay to go ahead and go with that. So this is a binomial setting. So now we can calculate. What we're interested in is the probability that no one wins. Well, if there is a 1 in 6 chance of winning, it should make sense that there is a 5 in 6 chance that you lose. I hope that makes sense because 1 plus 5 equals 6 and 6 divided by 6 is 1, which is 100%. Remember, our probability always has to add up to 1. So here is just me going through and showing this. So this can be in your notes of how we checked it. But now let's actually answer the question. All right, so we said there's a 5 in 6 chance that you fail. So what's the probability that all 6 of us lose? Well, we just multiply it. So if I lose times my friend loses times my second friend loses and my third friend loses and my fourth friend loses. 1, 2, 3, 4, 5. One more. And then we can do this on the calculator. You don't need to do this. So when I put this in my calculator, I got 0.335. And remember, to make it a probability or percent, you just move the decimal place 2 places to the right. So there's a 33.5% chance that no one will win. And so that's just how we calculate that. We just multiplied all the number of people who lost. Now, we haven't actually done a binomial formula yet. This is just stuff we've done before. We've done the multiplication rule before. And the multiplication rule basically says we just multiply the probabilities to get the answer. Now, binomial can get very picky because now this is with no one winning. And it's going to change when I want, different numbers. So maybe I want the probability of 1 person winning or the probability of 2 people winning. So we have something called the binomial theorem. We're going to write this out. And we're going to say that the probability that x equals k. Now, k is just going to mean the exact number of successes you want. So that's what k stands for. Now, this NCK is a combination formula. So you've got to use your combination formula to do that. And N is your number of trials. And we're going to multiply it by the probability of success raised to the k power. And we've already talked about what k is. And 1 minus p is actually the same thing as failure. And we're going to raise that to the n minus k power. And once again, n and k are both there. And so p is the probability of success. And 1 minus p is the probability of fail. So let me kind of explain how you would do this problem. So if I'm going to flip a coin 10 times, and I know I want heads, so that probability is 1/2, and I want to get exactly 3 heads, we would plug this in like this. This would be my N, this would be my K, and this would be my P. So I would do 10C3 on my calculator, and then I would raise 1/2, which is my probability of success, to the K power, which is 3. And then I would do 1 minus 1/2, which of course is 1/2 here also, to the 10 minus 3 power, which is 7. In that case, kind of in the way. So then you would just plug this into your calculator. So once again, you need to have a calculator that can do combinations for you, because you don't want to have to memorize all these formulas, especially for a test. It's pretty easy to remember that we're just going to stick a combination on with probability of success raised to the K power, and then probability of failure raised to the N minus K. That's just something you have to memorize. Everything else you could do on your calculator. All right, so once again, we're going to go back to our Coke bottle or soda example. And it says we have a 1 in 6 chance of winning, so that's still our probability of success, right? So our P is 1 in 6. And we have 6 people purchasing, so N is 6. That's how many people are buying it. And the first question says, what is the probability that exactly one person wins? Well, for that question, I'm basically saying what's the probability, or K, is 1. So we are going to do 6C1, 1/6 to the 1 power. And then I'm going to go ahead and say that 1 minus 1/6 is 5/6, because I don't feel like writing all that out. Raised to the 6 minus 1 power, which is 5. All right, so I'm going to turn on my calculator, and I'm going to go to 6 Math, PRB, and I'm going to choose NCR, and I'm going to pick 1, and I'm going to hit enter. And that's a 6. Then I have 1/6 raised to the 1 power, which is just 1. And then 5/6 raised to the 5th power is approximately 0.401877. Now I'm going to just store this in my calculator, and I'm going to times it by 1/6, and I'm going to times it again by 6. And it should make sense here that those 6's actually just canceled out, so I really didn't need to put that in my calculator. We get this same number, 4018 blah 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 blah, which basically means 40.2% chance that exactly one of us will win if we play that Coke bottle game and we all buy a Coke. All right, so that is the first problem. And now it asks, okay, well, what is the probability that nobody or all 6 people win, I'm guessing is how I should say it. So that means my probability and my N doesn't change, but my K does. Now instead of just one person winning, I'm saying what happens, or what's the chance of all of us winning? Now, hopefully you think intuitively that that's probably not a very big chance. So let's see what we get. We have 6C6, probability of success raised to the 6th power, probability of failure raised to the 6 minus 6 power is 0. And if you remember from Algebra 2, anything raised to the 0 power is just 1. So you can put that in your calculator if you want, but it's just going to be 1. And so we're going to go to Math, PRB, and we're going to do 6 choose 6, or 6C6, and we get a 1 again. So we get a 1 here, we get a 1/6 here to the 6th power, and we get another 1. So hopefully you saw that right here, this thing is just going to be my probability. So on my calculator, I do 1 divided by 6, exponent to the 6th power, and this is what I get on my calculator. You may get something else. But it says 2143E -5. Please don't ever tell me that that's 214%. Now, I have had students in the past tell me that. This E stands for exponent, and that -5 is scientific notation, meaning you need to move this decimal place 5 places to the right. So that's 1, 2, 3, 4, 5. So that's the decimal. As a percent, the decimal moves back 2 more places, obviously. So basically, the chance of all of us winning is 0.002% chance. And we already talked about how unlikely it would be for all 6 of our friends to win. And this is actually how unlikely it is. It's 0.002 or less than 1% chance that all of us win. Okay, so once again, rewind the video and watch it if you need to, if you're not sure how to do the E -5. Anything that's like that means you have to move the decimal place that many places to the right. But then if we change it to a percent, we had to move it back 2 more, so that there were actually only 2 zeros in front of that 2. All right, so I went ahead and figured out the probability for all of them, and we already figured out 1 was 40%, remember? And here 6 are, you know, a bunch of zeros, the 4 zeros in front of the 2. And so I went ahead and plugged in the binomial for 0, 2, 3, 4, 5. That's how you get that, by the way. I just redo the problem over and over again with k is 0, k is 1, k is 2. And so I basically did this problem 7 times. These probabilities should add up to, guess what? 100%, because that's what they should add up to be. And I can create a distribution or a histogram again. And so once again, 0 is about 30%, so it's not quite up to 0.4. 1 was exactly at 40%. 2 was at about 20%. 3 was only at 5%. And then 4, 5, and 6 get smaller and smaller and smaller. Now, we had a name for graphs that look like this. It's not centered around the middle. Note that would be a normal or bell-shaped curve. But basically, all of our information is on the left-hand side, and on the upper values, our tail gets smaller and smaller. And so the name of our graph is always based on the direction of the tail. So since my tail is going to the right, this is actually called skewed right. So the shape of this graph is skewed right. Expected value can also be found from binomial settings. So when we did expected value from regular histogram or the regular frequency tables, we just multiplied the number of the amount up top by the probability of each happening, and then we added them all together. That can take a while. On binomial, the expected value is super, super easy. You just do n times p, okay? So come back to our problem. This was our p. This was our n. So if I want the expected value, I would just do m times p, so 6 times 1 over 6, and my 6's cancel, and so 1. So it should make sense that if 6 of you buy a bottle of soda and there's a 1 in 6 chance, they kind of tell you 1 in 6 chance that somebody will win. How many people do you expect to win out of 6? Well, 1. And so that is how we get expected value. Super, super easy calculation. You just have to memorize it, because if you don't memorize it, I'm going to put it on the test and somebody's going to miss a super, super easy question. All you have to do is multiply the number of people or things in the trial times the probability of success. All right, so let's practice. So we have 44% adults who have type O blood. This is for all my future doctors. We're going to do a medical problem. Okay? So, since they're telling you a probability, I'm going to label that as P. And I'm going to change it to a decimal because that's what we do. Suppose we choose 7 adults at random. Well, that's my N. What's the probability that all of them have 7? Or have all 7 of them have blood? Oh, that's my K. So it tells you again what number you want to do. Okay? So we're doing 7C7. We're going to do 0.44 raised to the 7 power. And 1 minus 0.44 is 0.56. And we're going to raise that to the 7 minus 7, which is 0. So once again, this is just 1 and this is just 1. So we're really looking at what 0.44 is to the 7th power. And notice that this wasn't a fraction. It wasn't 5/6. This one's actually a decimal, and you can do as a decimal. That's okay. So 0.44 to the 7th power is going to be 0.003, or basically 0.3%. So that was A. B says, what is the probability that exactly 4 people have it? Well, my P stays the same and my N stays the same. But now the K changes to 4 because I've changed how many people I'm interested in. So I do 7C4 now, to the 0.44 raised to the 4th power, and 0.56 raised to the 7 minus 4, which is 3. So you have to go to 7 and then NCR 3, and that's 35. And I'm going to times that by all these, and I'm not going to write all this out. But basically, we're going to hit times 0.49 raised to the 4th power times 0.56 raised to the 3rd power. And when I plug that into my calculator, I get 0.354. And so that's really 35.4%. Now, when it says create the table of distributions, what it really wants you to do is go back and do this formula over and over and over again. So we did it for 0, and we did it for 7, and we did it for 4. So it wants you to go back and plug in a 0, a 1, a 2, a 3, a 4, a 5, a 6, and 7, and get all of those values. And I'm not going to bore you with doing that. You should be able to figure that out. These formulas are not hard. You just plug in different numbers and write down all the probabilities. Then it's going to ask you to graph it. So once again, once you've got all the values, all 8 of them, because it's 0 plus 1 through 7, you're going to make a chart. And on the bottom is going to be 0, 1, 2, 3, 4, 5, 6, 7. And on the left-hand side is going to be your decimals, and that's what you're going to shade up to make a table. So like I said, I'm not going to go through all of that because I don't want to bore you. Okay, so a couple other things. A new problem. And we have one that's now talking about agriculture or seeds. So kind of read over that for a second. Okay, now let's see if you can decide what the different values will be. It's telling us that 85% of our seeds germinate. So the probability of success is 0.85. Miss Jones buys a packet with 20 seeds in it. That is my N. Part 1, what is the expected value? Because how many should I expect to germinate? Expected value is N times P. And so we're going to do 0.85 times 20. And that equals 17. So out of the 20 seeds I plant, it is reasonable to think that 17 of them will germinate if this is a true claim. Part B says find the probability that exactly 15 grow. Well, in this one, that means that my K has to be 15. So we are going to do N, which is 20, C, K, which is 15. The probability of success is 85 raised to the K power. And the probability of failure, so 18 or 85, 95, 100, that's going to be 15%. And since there were 20 minus 15, that would be 5. So you plug this into your calculator. Okay, so after I did all that mess, I get 0.1028. So basically 10.3% chance that 15 of them will. Once again, 15 is pretty close to my expected value, and 10% is not bad. And then C says find the probability that less than 2 will grow. Well, less than 2 means 0 or 1. So we're going to do the probability twice. So I'm going to do it once when k is 0, and then I'm going to do it again when k is 1. And I'm not going to write out the formula, but we're going to do 20C0, 0.85 to the 0, and 0.15 to the 20th. And then I'm going to do it again for 1, so 20C1, and etc. And do that. So go ahead and get your calculators out and start plugging those in. Alright, for 0, that's a ridiculously low number. It's like 17 zeros. And then some 3s. Then we do it for 1. So we do 20C1. And we're going to times that by 0.85 raised to the first power. And then we're going to times it by 0.15 raised to the 19th power. And we get another super small number. So basically we have 14 zeros. And then 37 is what it said. Alright, so when I add these two together, it shouldn't be any surprise to you that I'm going to have 15 or 14 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And the next two numbers are 3, 8. Because when I add 3, 7 and 3, 3, that 3 is going to make it go up and round up. Okay, so that's the probability that you get less than 2 seeds. So it's not very likely that if I were to grow mine and only 2 seeds germinated, that probably means I got a really bad pack, because it's not very likely that that happened if what they claimed is true. Okay, so most of the ones I'll assign you won't be quite so small, because that's kind of annoying to write that many zeros, but it gives you a good idea of how this works. Alright, so how do you do these problems? Well, you have to remember the n times p for expected value, and you need to look in the question for a hint of them saying expect. Because they may not say, what's the expected value? They may just say, what do they expect to get? That's not an opinion. It is the expected value question that they're asking for. And then you have to remember the NCK formula, or how to do it in your calculator if you're using that. And then the binomial formula. Once again, that's binomial right here. So you want to memorize it. We have a test coming up, like I said, because this is the last section in this chapter. So you want to start reviewing all the formulas and how to use them. It has been a while since we've done 8.1 and 8.2. You can go back and watch the video, fast forward through the boring parts, get to the stuff that you need to know. And it's a really good practice, especially with online lectures, to do that, because you have the ability to seriously go back and play it. It's kind of like if you had the ability to record lectures. You can go back and listen to what you need to hear. Alright, so I recommend doing that. Now, homework. It's very important that you do this homework, because if you don't practice and you try to take it for the first time on your test, you're going to bomb, because it's not going to work very well for you. Okay, so on page 412, numbers 59 through 63, these are pretty straightforward questions. And so you're going to be using binomial, or you're going to have to check to see if something is binomial. So remember those bins that we talked about. All right. So I'll just start you off. Like number 59. I won't do all of 59, but we could get started. Number A, or part A, just says show that the criteria is being met. That means to check bins. And when you check bins, you have to write a B-I-N-S like this, not sideways. And you're going to write across here. Don't just say yes or no. Never say just yes or no. Tell me what it is. So here, for example, it's asking if a dog greets or not. So a success would be a dog greeting you, and the failure would be not greeting you. So you're going to tell me what success and failures are. So I'm not going to do all of those. You can figure that out. But B, it says find the probability that exactly 7 of the 12 dog owners greet their dog, or dog owners greet their dog first when they arrive home. Okay? So this is going to be binomial. So 12 is the number of people we're testing, and we're trying to see exactly 7. And it told us that 66% is a success. And we're going to raise it to the k power, which is 7. And if 66% is a success, then 34% is a fail. And once again, that comes from 100 minus 0.6, or 1 minus 0.66. And then 12 minus 7 is 5. And you would plug that into your calculator. For C, it says find the probability that at least 5 of the dog owners. At least 5 means 6 or more. So you would do that for each of those. Now, if you guys have a graphing calculator, there is a command that could make your life a lot easier. So you're going to do 1 minus, and it's called Binomial CDF. And you would type in the number that you had, the probability, and then how many you want less. Well, since I wanted 5 or more, I would be checking the 4. And Binomial CDF, if you don't know how to get to it, but you do have a graphing calculator, you're going to go, this command right here is in second, and it's the button that says VARS. And you're going to scroll down until you see that Binomial CDF. Okay? There's one that says PDF. Don't pick that. It needs to be the C. So, for those of you who don't have a graphing calculator, you basically have to do this for 6, 7, 8, 9, 10, 11, and 12, and then add all those probabilities up, and it won't be a small number like the really tiny decimal like I did. But if you have a graphing calculator, your life got super easy because you just type that in, and it will give you exactly the probability. Binomial CDF always gives you the or less, never the or more. And so C asks for or more, that's why I did 1 minus. If you remember when we talked about less is usually what our charts give us, and then when it's or more, we just have to subtract it from 100 to kind of flip it the other direction. All right, so hopefully getting you started on 59 will help, and then there's some graphing on there and some more calculations of these things. So just make sure that you do your best work and really get ready for this test that's coming up. Hope you have a wonderful day.